As humans, we are painfully aware of our body's shortcomings, with a lower back and knees that can't really tolerate our bipedalism, and a processing center perched atop a pole for closer proximity to our sensors. We ride atop wheels to traverse land faster, and entirely lack the ability to fly without assistance. So why are we building machines that resemble ourselves, sticking them with many of the same shortcomings? There are so many possibilities. There are actually important reasons that explain this choice. At first, they might seem a bit intuitive, but after systematically laying them out, a larger picture emerges. The rationale for building robots in a humanoid form factor can be described through 5 key elements. Firstly, our infrastructure is built for humans, and specifically able-bodied ones. Something as common as a door handle becomes an insurmountable obstacle for the vast majority of non-humanoid robots. Our spaces are tied together with doors, staircases, and steps. Even the alternatives to these features, such as elevators, require manipulators with dexterity to summon. These barriers render many areas inaccessible to those who rely on wheels for movement, despite pushes for accessibility. A video has been making the rounds of a robot that can rotate its wheels into feet in an attempt to bridge this gap. But ultimately, the economic impracticability of rebuilding global infrastructure to accommodate an array of robotic forms makes adapting robots to our world, rather than vice versa, the more logical path. The second factor is generalization. A robot designed for a specific task will outperform a humanoid in that niche, but the humanoid is able to perform many different tasks. Take the task of retrieving a rock sample. For a very small rock, a specialist robot with better traction, smaller and more precise instruments for collection, and a built-in safe and controlled storage compartment would perform better than a humanoid robot. For a large rock, a stronger specialist robot with locking arms and a wide base for balance would likely outperform a humanoid design. However, a humanoid could use handheld tools and a discrete container for the collection of a very small rock, and operate a forklift or use a sled to transport a large rock. It's less efficient and reliable for these tasks than the specialist robots, but it's able to complete both and try a different strategy if the initial approach isn't working. It's economically unrealistic to design a new, highly specialized robot for every niche task we might encounter, though this approach makes sense for large-scale and repetitive use cases. The third reason is familiarity, as many of these robots are being designed to work collaboratively with humans in shared spaces. Whether designed for home or workplace use, robots are intended to be familiar and feel friendly to the humans around them. An important part of this familiarization is making robots look like us. Our brains are wired to form stronger connections to human faces and forms. We consider robots that resemble ourselves to be more complex and individual beings. This means the approach of humanoid robots is a double-sided coin. Anthropomorphizing robots may make friendship and acceptance easier, but it may also do the same for resentment and hate when these machines inevitably make mistakes and replace human workers. The fourth factor is undeniable and missing from a lot of conversations about humanoid robotics, and that is hype. Showcasing humanoid robots is a great way to capture excitement from the public and elicit funding from investors. They are inherently tied up in science fiction and past dreams of the future. For many, seeing a humanoid robot walk around and converse naturally is just much more impressive than watching a demo of a treaded firefighting robot, despite the humanoid's lower utility. But on that note, humanoid robots are also a way to display to investors robots' potential to automate jobs and directly replace human workers. The fifth factor is best described through a statement. Theoretically, one human robot can accomplish anything a single human can do. Now, whether robotics ever reaches this point, or if humans have some sort of unique essence, is not what this statement is trying to get at. It's attempting to point out just how much one being can accomplish. It's easy to think of a humanoid robot being constrained to a small geographic area and small scope of actions, but imagine a robot with the goal of retrieving an item from another continent. With the technology available today to individuals, this would be entirely possible. The field of humanoid robotics is currently in a rather weird place. Dexterity and design have vastly improved over the last 20 years, with better motors and new movement systems and new ways of training robots to move, but they're a bit stuck on being able to actually do anything by themselves. To be clear, there has been quite a bit of advancement here as well, but there are so many different companies, each making very vague claims, so it becomes very difficult to know of their true capabilities. Most recent gains have come from sim-to-real advancements, where researchers are able to train a virtual robot through physics simulations on a computer and transfer that motion to the real world. These simulations still cannot entirely accurately capture the way the real motors will interact. One example of sim-to-real working recently was Engine AI's robot walking very naturally, utilizing Isaac on the NVIDIA Omniverse platform. To some extent, robotics companies are focused on hardware right now, while waiting for better software to be developed. But on a baseline level, what would be needed in a humanoid robot, and what is currently available? Let's consider 3 simple tiers of capability. Level 1 includes 2 discrete processes, a body that can be remotely controlled, and a LLM that can be spoken to. Level 2 sees the LLM gaining some degree of control over the body, capable of ordering pre-programmed movements or sequences. Level 3 would see the LLM and movement system fully integrated with one another, allowing for adaptive and truly autonomous action. Right now, it seems like most robots are still at level 1 or 2. But there are plenty of demos out there of robots performing level 3 abilities, from Google Gemini Robotics and Figure Robotics, for example. Some companies are going for a blank slate, open source approach, where they provide a built-in LLM and very capable hardware, but really seem to expect the customer to adopt a more advanced software system when it becomes available. Others are working directly with companies to develop software that makes their robots directly useful to the specific company or organization. There are so many companies teasing and releasing humanoid robots that it's difficult to tell what's genuine innovation and what's entirely fabricated hype. I would love to make follow-up videos doing research into each of these hyped up robots if there is interest. Subscribe for more videos like this one.